So today's lesson is about Feynman diagrams. So what you're going to learn to do is to sketch and interpret simple Feynman diagrams. So Feynman diagrams are ways of representing particle interactions using simple diagrams. And they look a little bit like this. This is an example of a Feynman diagram. Now there are rules, and here are the rules. The Feynman diagrams tell you about the particles before the interaction and the particles involved after the interaction. They also highlight if there's an exchange particle involved, a boson, and they should tell you something about conservation. Now, the first thing we need to do is decide on a direction. The direction can be either from left to right or from down to up. It doesn't matter which. Now, there's no consistent protocol. Both are valid. And the reason for this is that the purpose of the Feynman diagram is to keep it simple. It's a simple representation, like telling you a story about what's happening. So don't worry too much about choosing the right direction, because either are valid. The second thing is to use the correct notation. A straight line in the direction that you've chosen represents a matter particle. If you've chosen from left to right and you want to describe an antimatter particle, you would draw the arrow in the opposite direction. So matter particles go from left to right or from down to up if you decided to use that direction. And antimatter particles will do the opposite. Exchange particles are drawn with a squiggly line. So if we have a look at this picture is using the left to right direction, and you can see that there's a matter particle and an antimatter particle meeting, which then generate a boson, an exchange particle. Any ideas what this could be? Have a think. This picture represents an annihilation, matter, antimatter, making an exchange particle. This is the same interaction, but outlining the difference before and after the interaction. We can have exactly the same diagram, but drawn using the bottom up. Before, after. Okay, does that make sense? I hope so. Now would be a good time to take notes on the assignment. If you need a little bit more guidance, you can use these videos that are on the presentation to help you. I'll put the links on the assignment as well. Now let's have a look at some more complex interactions. The most common Feynman diagrams relate to beta negative and beta positive decay. In beta negative decay, I'll just remind you, a neutron becomes a proton plus an electron and an antineutrino. We've come a long way since I first mentioned this. You've learned about quarks and neutrinos, and you now know that the reason why the neutron becomes a proton is because something happens to the quark arrangement for these, and we'll look at that in a moment. You also now know that the neutrino and the electron go hand in hand. Now this is a Feynman diagram for this reaction. It's brilliant, isn't it? Okay, as you can see in this diagram, they're using bottom, top in this direction. And so what we have is a neutron. Now how does a neutron become a proton? A neutron becomes a proton because a down quark changes into an up quark. And so we show our matter particles are 3 matter particles, which continue being matter particles. However, there is a release of a W minus boson. You must remember that for this particular reaction, the beta minus, the boson involved is the W minus. Easy to remember because it's all minuses. And then what's given off, right? We're still going up. Oops. We're still going in the up direction. And what's given off is a beta and an antineutrino. Now this is an antiparticle, and so it goes down. Now the important thing is that you don't draw these arrows in this direction down, because they weren't there before the interaction. Here is our before and after, this point here, and so everything above that point must represent after, must represent this side of the equation. Beta positive decay is very similar. A proton becomes a neutron, and a positron, and a neutrino. Sketch out what you think a Feynman diagram would look like for this reaction. And here we have the diagram. You have 2 ups and 1 down. That's our proton. One of those ups becomes a down, and as a consequence, this time a W plus boson is given off. We're still moving up, and this time a neutrino and a positron is given off. Notice that the positron is going in the opposite direction because it's antimatter. I hope this makes sense to you now. It's important to note that if there is a change in direction in a line, it signifies that the motion of the particle has changed, which if we go back to these, you can see that there is a change in direction. Okay. Similarly, these two move in different directions too. This one is another diagram, but for exactly the same reaction. Here we only have one of the quarks. The quark changes to an up quark. The boson moves, is given off, and we get your neutrino and your beta particle. This is a different diagram because here they're using left to right. But the change in direction is similar, as is the fact that these two are given off in 2 different directions. Very important, this time, this is our before and this is our after. And so you would never have this on that side. Okay, that's important. This is an interesting reaction. See if you can figure out what's going on here. I just threw this one in for fun. These are 2 quarks which basically interact with each other by swapping bosons. These 2 bosons annihilate to give a Z boson, and then as a consequence generate a muon and an antimuon and some electrons. But I wouldn't, an electron and a positron. I wouldn't worry about this too much. I just wanted you to sort of have a look at something completely unknown. Always consider conservation when looking at Feynman diagrams. It's important to make sure that you have conservation of charge, you have conservation of quark number and lepton number. These should be evident from your diagrams.